Welcome back. Today, we're diving into something pretty amazing, an invisible force that connects two things you'd probably never guess were related, electricity and magnetism. I mean, we all know electricity can light up a bulb, right? But did you ever think it could act just like a magnet? Well, let's find out exactly how.
Okay, so let's kick things off with a little puzzle for you. Picture a compass, the needle always pointing north. Now picture a simple electric wire. They seem totally different, right? But what if I told you one could actually make the other one move? How's that even possible?
So where do we even start to understand this link? Well, our story doesn't begin in some fancy lab with a perfect experiment. Nope. It all started with a complete accident during a university lecture. It's kind of funny how sometimes the biggest breakthroughs happen when you're not even looking for them.
All right, so picture this. The year is 1820. A scientist, Hans Christian Oersted, is in the middle of a lecture. He flips a switch for an electric circuit, probably to show his students something routine. But then he notices a compass on his desk, and its needle just moves. It deflects away from north, and just like that, with that one little twitch, Oersted accidentally discovered one of the deepest secrets of our universe.
And, the impact of that one little observation, it was huge. This wasn't just some cool trick for a classroom. It was the first time anyone had proof that electricity and magnetism were like two sides of the same coin. That one discovery, it literally opened the door for everything from radios to televisions, all the tech we use today.
Okay, so we've got it. Oersted proved there's a connection. An electric current creates a magnetic effect. But what does that look like? I mean, this force is totally invisible. So how in the world are we supposed to see it?
Well, there's a really clever trick to see the invisible. If you take a magnet and just sprinkle some iron filings around it, something magical happens. They don't just land in a pile. They instantly arrange themselves into these beautiful curved patterns, almost like they're tracing invisible lines in the air. And that's exactly what they're doing. We call these magnetic field lines.
So, this whole area around the magnet where it has its power, that's what we call its magnetic field. You can think of it as its personal space, where its force can be felt. And those iron filings? They're basically drawing us a map of that invisible force.
Now, these lines aren't just random scribbles. They follow some very specific rules. They always flow out of the North Pole and curve around to enter the South Pole. And get this, they even continue inside the magnet, making a complete closed loop. Where you see the lines packed really close together, that's where the field is the strongest. And the most important rule of all, two field lines can never cross each other, ever.
Okay, so that's a regular magnet. But let's get back to Oersted's big discovery. Remember, an electric current creates its own magnetic field. And the really cool part is, we have a way to predict exactly what that field is going to look like.
So believe it or not, the shape of the wire is what decides the shape of the magnetic field. If you have a simple straight wire, the field lines are just perfect circles around it. But if you coil that wire up really tightly into something called a solenoid, whoa, something amazing happens. The field inside that coil becomes super strong and straight, almost like a magnetic laser beam.
And here's the absolute coolest part. That magnetic field from the coiled wire, it looks almost identical to a normal bar magnet. It has a north pole, a south pole, the whole deal. But there's one massive advantage. You can turn it on and off whenever you want. That right there is the basic idea behind every single electromagnet.
Okay, knowing the shape is great, but we're missing one crucial piece of the puzzle. Which way are the field lines going? Are the circles clockwise? Counterclockwise? We need to know the direction.
Luckily for us, there's a super simple trick for this. It's called the right-hand thumb rule. You can even try it right now. Imagine you're grabbing the wire with your right hand. Just point your thumb in the same direction as the electric current. Now look at how your other fingers are curling around the wire. That's it. That's the direction of the magnetic field. So simple, right?
Okay, let's recap. An electric current makes its own magnetic field. We've got that. So, what happens if we take that current-carrying wire and put it inside another, stronger magnetic field? Let's say from a big horseshoe magnet.
Well, this is where the magic really happens. Things start to move. See, the two magnetic fields, the one from our wire and the one from the big magnet, they start to interact. They basically push against each other. The result is a real physical force on the wire, making it jump or move. Look, you can see the rod is actually being pushed. We've just turned electricity into motion.
So of course, that push isn't just random. It moves in a very specific direction. And just like before, you're probably wondering, is there a trick to figure out which way it's going to go? Yes, there is.
This time, we're using our left hand. It's called Fleming's left-hand rule. So take your left hand and point your first finger, your middle finger, and your thumb so they're all at right angles to each other. Got it? Okay. Your first finger is for the magnetic field, and your center finger is for the current, and your thumb will show you the direction of the motion or the force. This is literally how every electric motor in the world works.
Now, I know this all sounds a bit like high-level physics lab stuff, but I promise you, this is happening all around you right now in your own house. Let's bring this all home and talk about the wiring in our walls.
So, here in India, the electricity supply to our homes usually has a potential difference, or voltage, of 220 volts. This is pretty standard, though it can be different in other countries.
And that power comes in through 3 different wires, and they're all color-coded so we know what's what. There's the red one, that's the live or positive wire. Then there's the black one, the neutral or negative wire. And finally, you have a green one, and this one is super important. It's the earth wire, and it's all about keeping you safe.
So why is that green wire such a big deal? Well, think about appliances with a metal body, like your fridge or a toaster. If something goes wrong inside and the live wire accidentally touches that metal casing, that's incredibly dangerous. But the earth wire provides an escape route. It gives all that dangerous current a path straight to the ground, preventing you from getting a nasty electric shock. It's not an exaggeration to say it's a lifesaver.
So, wow, what a journey. We started with an accidental discovery in a lecture hall and ended up right here, talking about the wiring in our own homes. We've seen for sure that electricity can create magnetism. But that leaves us with a huge question, doesn't it? Can we reverse it? Can a magnet create electricity? Let's think about that.